we're going to go over how to both identify and later graph exponential functions. So let's first review a linear function. An example of a linear function will be something like this: y equals 3x plus 1. So this number in front, 3, could be any number, and it could be plus or minus any number, including 0. So those are examples of linear functions. And then to recognize a linear function as a table, we are adding the same value to y every time. And then most important is, when we first learned about linear functions, this wasn't true, but for what we're going to do in this lesson, we want to make sure that the x values are consistent. It's especially important for the exponentials. So what that means is, if we look down here at 4, the x values go up from 2, 4, 6, 8, so we're counting by 2 every time. Or on number 6, 0, 1, 2, 3, so it's going up by 1 every time. So those are, the x values are changing consistently. All right, for the exponential function, this is the new part. For the equation, it's going to be an exponential function if the variable is the exponent. And as a table, instead of adding the same value every time, we're going to multiply by the same value. And then we'll need this later, not right yet, but order of operations, just a reminder. When we do order of operations, we have to do exponents before we do any multiplying. Okay, so the first set, we're going to identify these as either linear or exponential. This first one looks similar to the linear one, where we've got a number in front times an x, and then in this case it'd be plus 0, so this is linear. Number 2 is exponential because that variable is in the exponent. And then number 3 is another linear, because again it looks very similar to that linear example that we wrote up here, where it's some number times x, and again this would be plus 0. Okay, so pretty easy to tell for the equations. And instead of remembering both, if you just remember that if the exponent is the variable, it's exponential. So the other ones then would be linear, especially with these directions. It's got to be one or the other. It's a little bit harder to do in a table. I want to go, how am I going from 4 to 16? Well, I can add 12, but then if I take 16 and I add 12, I don't get 64. So then adding 12 didn't work. So then it can't be linear because I'm not adding the same thing every time. So instead, I could also take 4 times 4 to get 16. And 16 times 4 is 64, and 64 times 4 is 256. So I'm multiplying by 4 every time because I'm multiplying by the same value. That's exponential. And if you're having a hard time getting to that value, how do I know I'm multiplying by 4? One way that you could check is you're going to divide backwards. So exponentials, we divide backwards. So you take maybe the 64 and divide it by the number right before it, 16. If you put that in the calculator, you're going to get 4. And you can check linear by subtracting backwards. So if you remember, we did y2 minus y1. If you want to find the slope, we add the x part in. So in this one, I could divide backwards, 7 divided by 3. But then if I do 11 divided by 7, I get a different answer. So I'm not multiplying. So instead I can do 7 minus 3 is 4. And 11 minus 7 is also 4. 15 minus 11 is also 4, which means I'm adding 4 every time. So since I'm adding every time, that's linear. And I'm going to use the calculator shortcut on this one. So again, I'm going to do this dividing backwards. So take the second y number divided by the y number right before it. So I can take negative 6 divided by negative 2. And we get 3. And I need to make sure that stays consistent. So then I can do the next one. I can do negative 18 divided by the one right before it, negative 6. And again, that's 3. And then we check the last one, negative 54 divided by negative 18. And yep, that's 3. That means I'm multiplying by 3 each time. Since I'm multiplying by the same value, that is exponential. And then for this next set where it says evaluate means we're going to solve for the given value. So for example, number 7, it says x equals 2. So I'm replacing that variable x with 2. So I'm going to have y equals negative 2 times 3 to the second. And then you can put it in the calculator or we can solve it by hand. If we solve it by hand, this is where that order of operations comes in, that we have to do our exponents before we can multiply. So I would have to do 3 squared first, which is 9. Then I can multiply by negative 2, and we get negative 18. And number 9, we're replacing x with 4. So this one's in function notation. Replacing the x with 4. So this just tells us, this part here just tells us that I'm going to evaluate this function when the x is 4, because it tells me x is 4 here. So this is just kind of information purposes only, and we don't actually use this part here in our solving. So when I start solving, I'm only looking at what comes after the equal sign. But again, exponents first, so 1/2 times 2 to the 4th is 16, and then 1/2 times 16 is 8. Number 10, we're plugging in x is 3. So order of operations says we have to do exponents before adding, but I can't actually do my exponent because my exponent is this whole thing. It's 3 plus 1. So we actually have to simplify that exponent first to find out that exponent is actually 4 before I can actually take that exponent and find that 2 to the 4th is 16. In number 11, we're substituting x as 2. So I'm going to solve this function when the x is 2. So again, this is information purposes only. Right here is information only. 5 times 3 to the second plus 1. So again, this part is information only, so it doesn't actually affect our solving. Exponents first. 3 squared is 9. And then next in order of operations, we have to multiply before we can add. So 5 times 9 is 45. And then we can add last, and we get 46.